let's practice just a little bit more with this 73B scientific notation stuff, looking at a risk per person problem. So this is a table with leading causes of death. This is pretty old data. It's 2011, but we're just going to work with the U.S. population from that year. So it was around 311 million. I think it's a little smaller, but close enough. So we see that there are 10 different causes listed here. And we're going to do some calculations. So the first question is, assuming the U.S. population is 311 million, what is the empirical probability of death by stroke during a single year? Now, when you see empirical probability, this just means the ratio using the exact data that you have. So this is the risk of death by stroke. And when they say this, you're just thinking per person. So what we need on the top of our ratio is the number of deaths from stroke. So that is 128,900. And then on the bottom, because we want per person, we need this, we need to list the number of people. So 311 million. So you can add in all your zeros. You can use scientific notation. You can actually use another version of scientific notation, which your book doesn't recognize, but other people do, that this is 311 times 10 to the 6th, if that's a little easier for you to type in. So people really struggle when there's a lot of zeros keeping track of what's going on. So if that's not you, just ignore us, but some of us have that problem. So this is around 0.000414. So we've already said we don't handle real small numbers well in our brains. There's a small number. That's what we get. That's the empirical probability, the risk per person. Now let's practice putting this in scientific notation. I noticed that that number is less than 1. So that means I'm going to use a negative exponent. So the first thing I'm going to do is identify what my number would be. So I'm going to go along until I find a number between 1 and 10. So that is 4. The rest of my value will be as the decimal. I'm going to put in my scientific notation, so times 10 to the. I've already decided this is going to be negative what? So remember, negative represents how far your decimal point has moved from the original problem. So originally it was here, now it's here after the 4, so that is 4 places. Now, let's convert this value to deaths per 100,000 people. I want you to practice this again. We can work with either of these starting numbers, and then we are going to multiply them by 100,000. Because remember, this is really times 100,000 over 100,000 to give me a number per 100,000. So I don't really get this per in the top number. I get it in the bottom number that I'm technically not writing. All right, so this would... this is actually 1 times 10 to the 5th. So I see this is negative 4. This is positive 5. So there's more positives. This is going to end up increasing this from 4.14 to times 10. Oops, and I didn't write it. Yeah, sorry. All right, let's try this again. So this is going to leave me with 41.4 per 100,000. And again, I ended up with an extra because I had 5 tens and negative 4 tens, which left me with 1 10. Just to kind of put all of that together. You can just multiply on your calculator. It's fine. So another thing we could do from this table is calculate the risks compared to other things. So here the risk of death of stroke is about blank times greater than the risk of death by kidney disease. So what we're going to do is we need to divide the risk of death by stroke by the risk of death by kidney disease. Now, we can calculate both of these as we did in part A. But I want you to think about that. In both of those cases, you would divide the number of deaths by the total population. So this would be number of deaths divided by population divided by the number of deaths from something else by population. So while the number of deaths would be different for the top and the bottom because they're different diseases or different causes, the number of the population would be the same. So really all I need for the top number is the number of deaths by stroke. So looking back up at our table, see if you get what I got. I got 128,900. Pause it and check. And then on the bottom, the number of deaths by kidney disease. So here's a chance for you to practice one we haven't grabbed from the table before. Find kidney disease, find the number of deaths. We get 45,700. So when I divide those, I get around 2.82. And remember on your homework to check how they want you to round those. If they say 2 decimal places, we're great. If they say 1, we'll change this to 2.8. If they say a whole number, we'll say 3. Whatever we're asked to do, we will do. Because that number is more than double, but not quite triple, right, is where that value came from. The worldwide risk of death by stroke is 7.119 times 10 to the third. So remember, risk of death is the empirical probability per one person. And there was 5,528,232 deaths around the world from stroke in 2019. So we're going to write both of these values in scientific notation and then compare them to the data we have here. Now, it is important to note that we are comparing these for 2 different years, but we're going to assume they're close enough that there's not enough that has changed that we're worried about. So this is currently in scientific notation, so it's going to standard form. I recognize right now that this number is less than 1, so I'm going to start with 719. 7119. The old decimal point was after 7, so I'm going to move it to the left to get a smaller number 3 times. So 1 brings me in front of the 7, 2 adds me a 0, 3 adds me another 0, and then I write the decimal point and throw in a 0 for a placeholder. So this is the risk of death by stroke in standard form. So we've got it in 2. Let's also do the deaths to scientific notation. Not technically, it is. The decimal point is right here. And if I want a number between 1 and 10, it's going to go right here. I am also going to, in this process, round it a bit. Watch, you may not always be asked to do that. But I'm going to change this just to 5.5 because otherwise there's really not much benefit to standard notation. Times 10 to the, this number is larger than 1, so I'm going to use a positive exponent to represent the fact that this has moved 1, 2, 3, 4, 5, 6 places. Some people also interpret this exactly as million. So this is 5.5 million, which is what we saw from our problem. So let's compare the risk of death from the U.S. to worldwide. So number of deaths isn't going to let us compare it. We don't have this in deaths per 100,000, though we can calculate it, but we do have both of them in scientific notation, both empirical probabilities and standard form. So in standard form, the U.S. one was this. In scientific notation, the U.S. one was 4.14 times 10 to the negative fourths. So we're comparing these two and recognizing that this is a smaller number because it has more decimal points after 0, or more zeros after the decimal point. Or we're comparing these two and recognizing that this is a smaller number again because there's more decimal points and more zeros after the decimal point. The risk of death here is lower. You know, we are a country with medical care, and there are a lot of countries around the world without really that much medical care. So that's probably the differences we